Today, we're visiting the INGPULS Company in Bochum. It produces nickel-titanium shape memory alloys used in medical devices. In this interview with Dr. Burkhard Maaß, we find out how SMAs work and in which areas they're being used. Shape memory alloys are functioned metal materials that remember the shape they were given during the molding process. That means I can reshape these metals, and once I heat them or bring them to the respective transformation temperature, they remember their original shape and are able to deliver a high work output. In doing so, I'm able to convert heat into mechanical work or vice versa. Shape memory alloy processes trigger thermodynamic coupling. They exhibit several additional material properties compared to other materials. Shape memory alloys are functional materials with the highest energy density today. That means they are able to provide a maximum work output per unit volume. That's the fundamental difference between them and construction materials such as steel or aluminium, which only have to bear loads. Meanwhile, alloys fulfill an actual function. That's why these materials are also called smart materials, functional or intelligent materials. There are multiple shape memory alloys that exhibit different mechanical and functional properties. INGPULS has specialized in nickel-titanium alloys. Nickel-titanium alloys are produced using a process chain that starts with a primary shaping process. Primary shaping pertains to metallurgy, where the raw materials, nickel and titanium, and other adaptable alloying elements are melted. They can subsequently mix in the liquid state. When they are cast and solidify, they bond and exhibit these unique properties. Next is a thermomechanical treatment that consists of forming steps. You can use various types of forming processes such as forging, wire drawing, and shaping. In this case, geometry and microstructure are adjusted to where we ultimately generate the properties we would like to see. In the liquid state, nickel-titanium can be very reactive because of the titanium. That's why we have to make very special arrangements and ensure high purity during the melting process, avoid any impurities, and also warrant the accurate control of the process parameters. It's also crucial to precisely adjust the alloy because the material is very sensitive to changes in the alloy composition. This means that if I don't properly adjust the nickel to titanium ratio with the initial weight, I might get the wrong transformation temperatures in the end, for example. This is very important, especially when it comes to components that are used in medical technology. The alloy needs to be perfectly adjusted for the material to serve its purpose in the end products. The field and purpose of use later on also play a decisive role. That's also why there are different production processes. Typically, we first produce semi-finished products. Initially, those are rods, wires, tubes or sheets that are subsequently processed to produce components. That might be a stent for applications in medical technology, for example, or other implants. It might also be catheter guide wires. Other industries use this material to produce spring actuators, for example. These are springs that generate a force and tread a path at a specific transformation temperature and subsequently fulfill a function as a release mechanism or a thermostatic valve, for example. Nickel-titanium shape memory alloys have actually been well established since the 1990s, and the main product and the most commonly used product is the coronary stent. A stent is a coronary artery-supporting tube-shaped device that is implanted via minimally invasive surgery. That's to say, it's compressed and inserted by using a catheter system and placed at the desired location. There it's released and unfolds on its own because it has shape memory ability. The stent then connects to the artery on the inside and supports it by compensating for or counterbalancing a narrowing or blockage. Implants, stents, catheter guide wires as well as dental wires are made from shape memory alloys. They can even be used for spinal implants. However, shape memory alloys need to meet special requirements when they're used in medical devices. For stents, for example, we must develop a component that's not being attacked by the body and does not dissolve in the bloodstream. Another crucial aspect is nickel release, since the material contains a lot of nickel. These are all questions you need to address. After all, this type of component is designed to remain inside the body for several years. A stent gets bent with every heartbeat because the blood vessel dilates once at the same time. The job of product developers is to design a geometry that can be deformed once with every heartbeat and can subsequently withstand this permanent load.
Die dann eben dieser Dauerbelastung standhält.
As a cross-sectional technology, shape memory alloys can not only be used in the field of medical technology, but also in many other areas. As a material, they could capture new markets and form the basis of several new processes and technologies.